Here's an intro to experiment 7, which is calorimetry. What we're doing in this experiment is using a coffee cup calorimeter to measure the transfer of heat between different substances. So in part A, we're taking a hot metal and putting it into water, and we're transferring energy from the hot metal to the water. We're recording temperature changes, and the point of part A is to find the specific heat of the metal. And then part B, we'll be using sodium hydroxide and a couple of different acids, and we'll put them together in the calorimeter. And once again, we'll watch a temperature change. And here we're looking for the heat that is either absorbed or released during that reaction. In part C, we're dissolving an ionic compound or a salt into water, and we're watching a temperature change to see whether that dissolution process is endo or exothermic. You'll notice all throughout the lab manual that we see the same equation over and over again. Q equals M times specific heat times delta T. So Q is always our heat. So it's how much heat is being transferred. M is going to be your mass. That may be of the metal, of the water, of the solution. We'll see all of those different options. Specific heat a lot of times is seen as little c, but specific heat is a set value for water, for metals, for any pure substance or solution, there's a specific heat. And then delta T is always going to be your final temperature minus your initial temperature. So we're watching some temperature change, and that's what's going to allow us to calculate the heat transferred. And then another super important concept for calorimetry is this right here, where there's always going to be two sides of what we're measuring. There's going to be some solution or substance that is absorbing the energy, and some substance or solution or reaction that's releasing the energy. So there's always going to be two sides of what's happening inside the calorimeter. And however much heat is being transferred, one is going to be absorbing it and one's going to be releasing it. And that's why we have a negative sign here. So we'll see all of these as we go. The videos will show you the procedures and talk through those. What I'm going to do is go focus on the calculations for you for a minute. So you'll do all of the pre-labs. And then in experiment 7, data sheet. So here for part A, what we've done is we have taken a hot piece of metal and put it into water. So here, once again, we are going to be focusing on two equations. Q equals mass times specific heat times change in temperature. We see that our mass of metal will be given here. And I'm not going to give values, you'll get those from the video, but we'll just kind of label all of the different variables. Then you've got the metal that's in boiling water, and it's in boiling water long enough to where the metal is assumed to have the same temperature as the boiling water. So this is actually going to be the initial temperature of the metal. Okay, the mass of the calorimeter, that's going to be your coffee cup. It's a styrofoam cup. And then we've placed water in it. And so then we'll subtract these two values. We'll use this and this to calculate the mass of just the water. So I jumped ahead to water for a minute, but that's the mass of the water. So you can see the two are separate. The temperature of the water in the calorimeter, that's the initial temperature of the water. Now here it says maximum temp of metal and water. So what's going to happen in the calorimeter is the hot metal is going to transfer its energy to the water. And they are at some point going to plateau at the same temperature when they equal each other. So this right here is actually the final temperature of metal and of the water. So whenever you're looking for temperature change, you'll go find final minus initial. So for water specifically, this will be your final water, and your initial water was labeled right here. So you use those two values to get to the temperature change. Heat gained by water. Anytime you see that word heat, that's meaning that we're trying to find Q. So here's our equation again. We're looking for heat of water, which means we're going to use specific heat of water, which remember that specific heat of water is 4.184 joules per gram degrees Celsius for water. So we'd plug that in for our C. Our mass of water we have right here. And our delta T of water we've already found. So we should know C, M, and delta T, which means we can find Q of water. And then what we have to remember is that second equation that was super important, which is if we know how much energy the water has gained, then that means we also know the amount of energy the metal has lost. So whenever you find the heat gained here of water, if we just reverse the sign and make it negative, then that's the energy that the metal lost. So if we look at this equation up here and we focus as a metal now, we know the Q value for the metal. We know the mass of our metal because it's right here at the top. We are looking for C. So down here it says we're looking for C of the metal. Delta T right here, once again, it's going to be T final minus T initial like always. And remember, this is the T final of the metal here. And here's the initial temperature of the metal here. So we can subtract to get that delta T. So we will know everything in this equation except for C. And that'll allow us to calculate C for the metal. So that is part A. Part B, so here you will get this data from the video. And hydrochloric acid, I've just provided data in the info sheet. So you'll have data for this trial and data for this trial just from different places. The base is the same, but the acid is different in each. So what we're trying to find here is whenever these reactions take place, do they absorb or release energy and how much energy? So here you'll be given that you're starting with 50 milliliters of acid in both scenarios. So what I'm writing here, you don't need to transfer to your notes. Or into your lab manual. I'm just going to run through quickly and point out some stuff. So you're starting with 50 milliliters of acid and 50 milliliters of base, okay? The temperature of the acid you'll be given, so you'll have a temperature of your acid. You'll also have your initial temperature of your base. Those will both be given as data points. So what you'll do is use those two to average here for your initial temperature of acid and base. So you'll take those two temperatures and average them to get your initial. And then you'll look at the graph that's provided and you'll find what the maximum temperature is at the end. So what it'll look like is you'll see a curve that looks like this for the reaction. And here will be your initial temperature of your base, that's where that'll come from. And then here will be your final temperature. That's the maximum temperature of the neutralized solution. So you'll be able to calculate a change using these two, because here's going to be your TF and here's going to be your TI. So we'll know the temperature change. We'll use those to get here. Remember to watch sig fig rules. Now volume of final mixture, we already said we used 50 and 50. So we know that the total is going to be 100.0. And here what this is telling us is that the solution has a density of 1 gram per milliliter. So if we have 100 milliliters of solution and our density is 1 gram per milliliter, that means we can also safely assume that we have 100 grams of solution. We're also making the assumption that the specific heat of mixture is the same as the specific heat of water. So this is going to be 4.184. the same as water. And then for heat of solution, you're going to do the same equation we've been seeing over and over. If we're looking for heat, we use the specific heat, which we now know, 4.184. The mass, we also know is 100. And our delta T, we've found right here. So we know all of those, we can find Q. That's going to give us heat. Then we've got to work our way to what's called enthalpy, which is the delta H down here. So if you look at units, this helps you a lot because we currently are in joules when we're talking heat. What we need to get into is kilojoules per mole of water. So the first step is we're going to take our joules. So we'll take our value from here. That'll be joules. And you'll convert it to kilojoules by dividing by 1,000. And then we need to divide by our moles of water. And what we are told here in your lab manual is that you have produced 0.050 moles of water. So once you do joules to kilojoules, you'll divide that whole number by 0.050 moles because that'll give you kilojoules per mole. So that's how you'll find enthalpy for both of those reactions provided there. Okay, and then part C, we're looking for enthalpy of solution of a salt. So we are taking a salt and we're going to be dissolving it into water. Here for part C, we'll be dissolving a salt or some ionic compound into solution, into water. You will get all of this data from a video that's posted. So you'll be given the mass of the salt. And then you can calculate moles using molar mass of that salt because it'll tell you who the compound is. So you can use molar mass to get to moles. And then you'll also be given calorimeter alone, given calorimeter in water, which you can use these two to calculate the mass of just the water. Okay. Mass of solution is going to be the mass of water plus your salt, which you know both of these because here's your mass of water, here's your mass of salt. So you're going to add those two together to get your mass of solution, which is what you want to be using. Okay, then you'll also see a graph that's provided in your data. And it could be exothermic or endothermic. But here, if we're watching the graph, we'll see our initial temperature will be whatever the original temp is, and then the final will be down here. We can put those there and get our delta T by subtracting. So what we can do is heat of change of solution. We are going to use the same old equation, Q equals Cm delta T. Really quickly, I'll just mention that the specific heat is still going to be assumed to be the same as water, 4.184. Mass, you're going to use the mass of the solution that you just calculated by adding the water and the salt. And then change in temperature you got from the graph. So you know all of those values. So you're going to find Q. Now the really important thing here is that's the heat of the solution. So the solution could have absorbed or released energy based on its temperature change. So whenever we switch over to the enthalpy of reaction, what we have to understand is if the solution gained energy, then what that means is the reaction has lost energy. Meaning it's exothermic, and it'll have a negative delta H. However, if the solution lost energy, that means that the reaction actually gained the energy. So the reaction is doing whatever the solution, the opposite of the solution. Because if the solution's gaining energy, that's because the reaction is producing it. So here from your heat to your enthalpy, you need to switch the sign. So if you get a negative Q here, then you're going to get a positive delta H here. So make sure that your signs get switched. And then once again, you're kind of doing the same thing as last part B. You're going to change joules to kilojoules. So down here, you'll take your joules, you'll change to kilojoules, and then you need to divide by your moles of salt, which you've already calculated up here. Your moles of salt you found here by using your molar mass. And that'll get you to your enthalpy change. And then you'll continue the lab and finish all the post-lab questions.